Hey guys, this looks like a fun one. We're trying to simplify this nested radical. It's the cube root of 9 times the cube root of 9 times the cube root of 9 times cube root of 9 going on forever. If you want to try it on your own, pause it right now because I'm going to solve it in 3, 2, 1. For the first step, inside of this outer cube root, we have this 9, which I'll color red, and this blue portion is the infinite radical. Let's split this up, and we have the red portion times the blue portion. We can rewrite this so that each of them have their own cube root. We can put the 9 right here and all the blue stuff right there. Now we have the same thing happening again. Under this double cube root, we have this red 9 and this blue infinite nested radicals. And we can do the same thing. We can copy this down, and this red 9 and this blue stuff are each going to have their own double cube roots. So we can put the 9 there and the blue stuff there. Now it's going to be the same thing again. We have this red 9 and this blue stuff that's going to go on forever. Each of these are going to have their own triple cube roots. So we have the red 9 here and the blue stuff there. And this is going to go on forever. And we showed that this nested radicals can break down into a product. So this ... can actually be brought on the outside. And this product pattern is going to continue forever. And now we can play around with this. Anytime you have x to the power of a over b, that's equal to the bth root of x to the a. So the cube root of 9 can be rewritten as 9 to the 1/3 power. This 3 is the same thing as this 3 here. And then we can do the same thing for this one. It's going to be 9 to the 1/3, which is the inner cube root, and that's going to be the power of 1/3. And we have the same thing for this one. It's going to be 9 to the 1/3 to the 1/3 to the 1/3. And the last one is going to have 4 of these 1/3, and this pattern is going to continue forever. And then using these notes for exponents, anytime you have x to the power of a in parentheses, whole thing to the power of b, it ends up being x to the a times b. So let's copy down the 9 to the 1/3, but then this next term is going to be 9 to the 1/3 times 1/3, which is 9 to the 1/9. And this one is going to be 1/3 times 1/3 times 1/3, which is 1/27. And the last one will be 9 to the 1 over 81. And then using these notes, anytime you have x to the a times x to the b times x to the c times x to the d, you can just add those exponents. So this is going to be 9 to the power of the quantity 1/3 plus 1/9 plus 1/27 plus 1 over 81 going on forever. And now we can evaluate this exponent. Let's put it in a red box and let's do our work in a red box. This is called a geometric series. Each term is exactly 1/3 times the term before it. Here are the notes for evaluating an infinite geometric series. This will always be true as long as the absolute value of r is less than 1. And r is the number we multiply by each time. So this is basically saying if you have some value, a is your first term, and your next term you multiply by r, and then for the next term you multiply by r again, and same thing for the next term. The infinite sum is equal to a over the quantity 1 minus r. So let's plug in our values. For each of these a's, we can plug in 1/3. And for the r's, we can plug in 1/3. And now we know this infinite sum. A is equal to 1/3, and then we're going to do 1 minus, and the r is equal to 1/3. This will simplify to 1/3 over 1 minus 1/3 is 2/3, and 1/3 divided by 2/3 is equal to 1/2. And this is our infinite sum exponent simplified. So in the place of this exponent, we can plug in 1/2. And now we can evaluate 9 to the 1/2. Using these notes again, we know that 9 to the 1/2 power is equal to the square root of 9, and the square root of 9 is equal to 3. And that is the answer to our question. This whole thing will simplify to 3. How exciting. So there is a more common, faster way to solve this. That's by setting the whole thing equal to x. So we say x is equal to this infinite nested cube root of 9s going on forever. But then for the next step, you'll notice that this portion of it is also an infinite nested cube root of 9s. So we can substitute x in for that. Then for the next step, we can cube both sides, and we end up with x cubed is equal to 9x. After that, we can subtract 9x from both sides, and then we can factor out the common term x, and then factor the x squared minus 9, which is the difference of two squares, can break down into x minus 3 times x plus 3. And then anytime you have something times something times something equals 0, it could be true if any of those somethings equals 0. So we can say either x equals 0, x minus 3 equals 0, or x plus 3 equals 0. And that'll leave us with 3 possible answers. X equals 0, x equals 3, or x equals negative 3. And then for the negative 3 and the 0, I'm pretty sure this answer has to be positive. So I think we can exclude those two values. I'm not exactly sure how to prove it rigorously. If anybody has any ideas, let me know in the comments. But from here, I'm pretty confident we can say x equals 3, which means our infinite nested radicals are equal to 3. So both methods got the same answer, and this method is the more common way to solve it. It's definitely faster, but I had a lot of fun going through the first method. And for the first method, we didn't have to introduce an x and an equal sign, and we didn't introduce any extraneous values. We only found the 3. Which way did you like more? And here's the next challenge problem. This looks like it's going to be a fun one. How exciting.